Hi, this is Dan Kernler, and this is part of my Calc 3 video series. Here we're working on section 15.6, where we're looking at tangent planes and how we can use the tangent plane to approximate a function near a point. So let's look at this first example. We have this function, and we want to look at the tangent plane near 3, 4, and use that to approximate the function at 3 600ths and negative 3 9200ths. So let's do the tangent plane here. Let's find out what it is. First, we need to find the partial derivative with respect to x. Let's see, this would be x squared plus y squared to the 1/2. So that's 1/2 times x squared plus y squared to the negative 1/2. And then chain rule, we're taking the derivative with respect to x. So we need a 2x. And that looks like that will be x over the square root of x squared plus y squared. The partial derivative with respect to y will be similar, except it'll be y over the square root of x squared plus y squared. Okay, now we need those evaluated at our initial point. So the partial derivative with respect to x at 3, negative 4 will be 3 over the square root of 9 plus 16. So that will be 3/5. And the partial derivative with respect to y at 3, negative 4 will be negative 4 over 5, negative 4/5. All right, so our tangent plane then will be, let's see, the partial derivative with respect to x times x minus 3 plus the partial derivative with respect to y times y minus negative 4 minus 1 times z. We need the z value there. Let's see, f of 3, negative 4, that'll be 5, right? 3 squared, 9 plus 16, square root of 25. So the z minus 5 equals 0. And what I'd like to do right now is solve for z and see what this would look like if we take this tangent plane and find z as a function of x and y. So let's see here, 3/5, you know what? Let's clear fractions, multiply everything by 5. So 3 times x minus 3 minus 4 times y plus 4 minus 5 times z minus 5. Let's see, 3x minus 9 minus 4y minus 16 minus 5z plus 25. Let's see here, that's convenient there. That looks like we get 3x minus 4y minus 5z equals 0. And if we solve for z, 5z equals 3x minus 4y, or z equals 3/5 x minus 4/5 y. So now the thing is, that is our tangent plane. And what we'd like to do is we'd like to use that tangent plane to approximate the function near the point where the tangent plane touches. So we are almost out of space, but we could say, let's go over here to our conclusion. Let's maybe do a different color here. F at 3.06 comma negative 3.92 will be a 3.92 will be approximately equal to the tangent plane z evaluated at 3.06 negative 3.92. And so that is, let's see, 3/5 times 3.06 minus 4/5 times negative 3.92. All right, let me open up a quick scientific calculator here in Desmos, and we have, what was it, 3/5 times 3.06 minus 4/5 times, it's too good with its recognition of parentheses, minus 4/5 times negative 3.92. So we get 4.972. 4.972. And let's actually calculate what that would be just in the function. And let's try that. That will be square root of 3.06 squared plus, I'm just going to call it 3.92 squared. Look at that. Very close. 4.967. So very close there. And the idea is because 3.06 and negative 3.92 is very close to 3, negative 4, the tangent plane does a pretty good job of approximating the function. Now it's interesting here, you'll notice that it's a linear approximation. The reason that it's called linear is because the function that we're using to approximate this is a linear function, meaning there's no squares, no square roots, no trig functions. It's x to the first and y to the first. So yes, it's a linear function, but it is a linear function of two variables, but it's still linear even though if it's like representation is a plane, a three-dimensional plane, but in terms of the equation, we call the equation linear. Okay, so the linear approximation here, let's see, let's switch our color back to blue, is essentially just the tangent plane. So you can write these formulas down, but all this is saying is the tangent plane. So if f is differentiable, the linear approximation to the surface is the tangent plane given by the equation, where essentially we just solve this, we solve the tangent plane for z. So it gives us the partial derivative with respect to x at a, b times x minus a, plus the partial derivative of y times x minus times y minus b, and then add to that the function, the z value, the function at ab. And then similarly, if we have a function of three variables, we can get a linear approximation there, and it's the same idea. The linear approximation is a function of x, y, and z. It's the partial derivative with respect to y at abc. No, y. The partial derivative with respect to x at a, b, c times x minus a, plus the partial derivative with respect to y at a, oh gosh. So what we can do here is we can approximate a function of two variables or a function of three variables by a linear equation in either two or three variables. And essentially this is just the tangent plane when it's a function of two variables. So if we have a differentiable function, the surface can be approximated at the point by the tangent plane, and that tangent plane, if you just essentially take the tangent plane equation that we have previously, and just solve that for, oops, this one, solve it for z. Solve it for z, you can see distributing the negative, you add z to the other side, you get z equals, and that is the equation for the tangent plane, which we're going to call the linear approximation of it. So that is the partial derivative with respect to x at a, b times x minus a, plus the partial derivative with respect to y at a, b times y minus b, plus the function at a, b. And if we have a function of three variables, the linear approximation for that at x, y, z will be the partial derivative with respect to x at a, b, c times x minus a, plus the partial derivative with respect to y at a, b, c times y minus b, plus, now we have a function of three variables, the partial derivative with respect to z at a, b, c at z minus c, and then we're going to add the function evaluated at a, b, c. So we're going to mostly do linear approximations for functions of two variables, but this could be extended. And in fact, this could be extended for functions of many variables. You can approximate them with a line near your initial point. And I should say a line. We can approximate them with a linear equation. Okay, next topic, differentials. This is another Calc 1 topic that we are now extending to multivariables. Hopefully you remember the idea from Calc 1. Let's say you have a particular C. You go up here, and yes, if we look at the tangent, oh, that's terrible. Let's try that again. So here's our function. We look at the tangent line there. And if x changes a little bit, in fact, I think we'll call this x. If x changes a little bit, call it delta x. This will become x plus delta x. Then there are a couple of corresponding changes that we want to focus on here. In fact, let's see if we can zoom in on that. See if I can make, whoa, a little more detailed drawing in here. To zoom back out later. So the two changes we have here is, one, we have this corresponding change in the function. So the y corresponding here to that change in x, the y changes some delta y. And then the tangent line also has a change. If we look at the tangent line, now it changes the same x, so we'll call that dx, and that's the same as delta x. But the tangent line changes some dy. And we can see here when we're close to the original x, the change in the tangent line is pretty similar to the change in the original function. The key here is that the change in the original function is approximately the same as the change in the tangent line. So how do we get the change in the tangent line? Well, it's just a little triangle there. You have the change in x and then the change in y. We'll call it the differential dy, the change in y. And so if you take the ratio of those, it looks, of course, like your derivative. That is, the slope there, the slope of that line is your derivative at x. Now this looks partially like that's just the notation for the derivative, but in this case we're treating the dy and dx as small change in x and a small change in y. And so to find dy, go back down for our equation, well, that is just the derivative f prime at x times dx. All right, so let's try to take a look at what this would be in 3 dimensions. So we have in the plane here, we have an xy, and then up above, I don't know if you can see, there's a little hidden dot there, that's f of xy. And what if we move in the xy plane from that point? Say we move a little dx, and then we move a little dy, and we're out here further in the xy plane. Oops, sorry. So we've moved a little in the x direction, we've moved a little in the y direction. There's a corresponding change in the function, and there's a corresponding change in the tangent plane. The function looks like it will have actually gone down. I don't know if we can see that. It looks like the tangent plane, though, would go up. So let me change those so we can see those. Let's change those to red in there. Here's our original one. And then whatever that z value is, it's a little hard to see, but the difference in the z value, that's the actual change in z. And then the difference in the tangent plane we'll call our dz. So the actual change in the function is approximately the same as the change in the tangent plane. So now the question is, how do we find the change in the tangent plane? And the idea is it's basically like ladders. If you have a slope in the x direction and you go over a certain amount, well, then you'll go up that same amount in the z direction. And then if you have a change in the y direction and you have a slope in that y direction, you'll continue up in the y direction. You'll have this over-up thing. If you can see there, you go over one way, so you go up, then you go over another way, you go up more. You end up with, like, if we can draw it on here, you're going to go up in this direction and then up even further to get the net change in the z direction. So what that is that's the slope in the x direction times the change in the x direction plus the slope in the y direction times the change in the y direction. And that is the differential. So let me fill that in on the next page here. So suppose f, oops, we can scroll back up so you see there. Suppose f is a differentiable function at the point. The change in z, as the independent variables change from xy to x plus dx and y plus dy, is denoted delta z and is approximated by the differential. Delta z is approximately equal to dz, which we said was the derivative, the slope in the x direction, multiplied by the change in the x direction plus the slope in the y direction times the change in the y direction. All right, in my class, in person, I usually say the same thing you are probably feeling right now. Like, this might seem plausible depending on how much you remember from Calc 1. To me, it seems a little fuzzy. Let's try to look at an example and see if it at least makes like not maybe that it'll all be clear, but at least like, oh, that actually is a pretty good approximation. So let's take a look here at this example that we have. We're not going to approximate the function value. We're going to approximate how much the function changes. Approximate the change in z. So delta z will be approximately equal to dz, which will be the derivative in the x direction evaluated at 3, -4, multiplied by the change in x, and the change in x is 0.06, plus the slope in the y direction at 3, -4, times the change in the y direction, which was -0.08. Our partial derivative, if you recall, in the x direction was x over the magnitude, basically. So the square root of 3 squared plus -4 squared. You can check back. If we scroll back up here, you can see there was that 3/5, the slope in the x direction, and the slope in the y direction was -4/5. So 3/5 times 0.06 plus -4/5 times -0.08, which will be, we have still have that calculator up. Let's see here, 3/5 times 0.06 minus 4/5 times -0.08. And so we get, it looks like, let's see here. Oh, it's not -0.08. It is positive. Okay, because we went from -4 to -3.92. So we can just erase here. Oh, it looks like my pen is a little bit off. That's why I'm feeling weird. Okay. And then it looked like we ended up with, what was it, -0.028. We get -28 thousandths. So that's the approximate change in the function. Let's just, for sake of comparison, let's find the actual change in the function. So delta z will be exactly equal to f at 3.06, -3.92, minus f at 3, -4. Let's see, I have that. Let's see, we'll pop that up. Square root of 3.06 squared plus, what was it, 3.92 squared. That's our 4.973. Oh. Yeah, 4.97. Oh, that's, what did we do last time? We got it higher than that. Anyway, so it's even closer than we thought. Didn't we say it was like 4.76 something? So 4.973, very close to the approximate change in the tangent line. And let's see, we're going to subtract the function value at 3,4, which is 5. So we get -0.027. Look at that. So close. We'll say this is still approximately equal to -0.027. So very, very close. The change in the differential is almost the same as the actual change in the function. If we want the percent error, it does say find the percent error in the approximation. So the percent error will be the estimate minus the actual over the actual. All right, so that is it for this video, and that is the end of 15.6 about tangent planes and then linear approximation, where we use linear functions to approximate functions. And we also can use the differential to approximate the change in a function.